welcome. My name is Abdul Hakim Muhammad Gubernur. My ID is 131192343, and my partner is Derajat Agung Nugroho with ID 131192242. We're from Group 19, and now we're going to explain about lattice difflection for our midterm take-home test. This presentation will be divided into two main parts: the introduction and the types. Without further ado, let's begin. Now I'm going to explain about the definition of lattice deflection. Lattice deflection is deviation from the ideal structure as represented by the space group. Now, how is it happen? You can see as the figure below. A perfect structure will show us an arranged crystal structure with without any deviation. The crystal deflection affect their properties such as mechanical strength, ductility, crystal growth, dielectric strength, magnetic hysteresis, conductivity, etc. But in reality, there are no such thing as perfect crystal, with every atom of the same type in the correct position. Because of that, all crystals have some defects. Defect in crystal may be confined to a point, length, surface, and volume. So that's why all crystals have some defects. The defects in crystal may be confined into a point, line, surface, or even volume. And now we're going to discuss about the types of deflection. There are mainly 4 deflection, as I mentioned before. First of all, there is point defects, line defects, surface defects, and lastly, volume defects. Point defects is occurring in a single point of crystal structure. Line defects is occurring in one-dimensional of the crystal structure. Surface defects is occurring in two-dimensional in the surface in the structural of the crystal. Surface defects is occurring in two-dimensional of the crystal structure, while form defects is occurring in three-dimensional of the crystal structure. Let's begin with point defects. When an atom is missing or an atom is in an irregular place in the lattice structure, the corresponding defects are known as point defects. Point defects produces strain in a small volume of the crystal surrounding the crystal, but does not affect the perfection distant part of the crystal. Because there is only one point defecting, the deflection is not affecting the whole structure of the crystal. It is just affecting around the deflection, like this or this or this. So, first type of the point deflection is vacancy. This is the simplest point defects in crystal, which refers to a missing atom at its site. Like we can see here, this is the perfect crystal structure. Well, here we can see there is a missing atom. So this is what we call by vacancy defects. The second type is interstitial. The definition is when an impurity atom tries to settle in the interstitial space between the parent atoms of the crystal without displacing. Then such a defect is known as interstitial defect. As we can see here, the orange atom is trying to get in between the parent atom. This is what we call by interstitial impurity. The third type of the point defects is substitutional impurity. The definition is when an impurity atom occupies the one of the position of the parent atoms of the crystal, then such a defect is known as substitutional defect. Like we can see here, this atom is different from the other atoms around it. This is what we call by substitutional impurity. When a different atom tries to fit in and substitute the parent atom. The fourth type of the point defects is Frankel defects. This is where an atom leaves its original lattice site and occupies an interstitial position on the same crystal. Usually this type of defect is observed in ionic solids, where size of anion is substantially larger than the size of cation. This is the perfect crystal structure, and this is the Frankel defects. As we can see, the cation is moving from its original lattice to an interstitial position in the same crystal. This cation right here is supposed to be here, but since it's moved to around here, this is what causing Frankel defects. After point defects, we have line defects. These are also called as linear defects or dislocation. This defect is happening in one-dimensional. So the definition is a dislocation in a one-dimensional defect around which some of the atoms are misaligned. So from this point, will be continued by my partner
Thank you, Bono,
Rajat.
for explaining the previous slide. And let me introduce myself. I'm Rajat Agung Nugroho, and I will explain the next slide. Okay, so Bono explained until line defects. And now we'll explain edge dislocation. Edge dislocation is one of the vertical planes that's not extended to full length but ends in between within the crystal. Then such a defect is known as edge dislocation. So it's over right here. We're actually creating from like halfway of here up to here is the edge of this the new edge dislocation. Okay, up to the next slide. We still have edge dislocation actually. So the screw dislocation are also known as Berger dislocation. This dislocation arise due to the displacement of atoms in one part of a crystal relative to the other part. So this is edge the screw dislocation. Now, surface defects, actually the regions of distortion that lie above the surface, having a thickness of few atomic diameters, are known as surface defects. Surface defects are two-dimensional defects that separate two regions of the crystal. So, surface defects would will have actually will have same atomic crystal, but just a different orientation. As you can see, the the difference in region, also difference in orientation, but same atomic crystal. Yep, over here. Yeah, these are the regions. And now we have external surface. The surface of a crystal itself is a defect. The surface atoms have formed bonds with neighbors only on one side, whereas the atoms inside the crystal form bonds with neighbors on either side of them. Yes, this is the external surface. Now, grain boundary. The most important defects in crystalline sample is the grain boundary. Grain boundaries are 2D defects in the crystal structure. A grain boundary is the interface between two grains of crystallites in a polycrystalline material. They tend to decrease the electrical and thermal conductivity of the material. So this is the grain boundary that separates the regions. 2. Now the last is volume defects. Volume defects, sorry, let me erase this. Volume defects in crystal are three-dimensional aggregates of atoms or vacancies. It is common to divide them into four classes in an imprecise classification that is based on a combination of the size and the effect of the particle. These are all the pictures of the volume defects. And this is the source we're using, and actually some from us. And thank you.